Okay. So, let's go ahead and get started. Windows was being bothered, so that kind of sucks because that means I can't use the board today, but we will work around it. So, I'll hand out the tests right now. Oh, I can't say.
Not 28.
Not 28. Okay. So we can go over any of the questions you guys want, and for the online students, you can email me to go over any questions if you have any confusion about them. If you took the exam online, did I not give you your test?
Yeah.
My bad. So for the online students, we graded your exams through D2L on that quiz. I'm not 100% sure how you can see the feedback, but I think you can like go back to the quiz and there's like a little tab next to it and you can click it and probably view the feedback like that. But again, I don't have the same view as the online students, so I don't know exactly how to do that. Yeah. So any questions about questions off the midterm? If not, we're just gonna go into lecture.
Question from the test.
Yeah.
Can we look at number 3D?
3D. All right. So this one, we have this command right here. We have the less than symbol with AB. We have E, F-G, H, and then piped into greater than symbol X, Y, Z. So we have three commands in this command line. And the syntax here, you know, it might not be completely valid if there's no command called A or B or E or X or whatever. But the syntax here is completely right, so you should be able to pick out what the command would be based off that. So, just water real quick. Shoot. That's not good. Sorry about that. So right here, we have less than AB. Does anybody have a guess as to what command is there? Somebody say something.
Just B.
Just B, right? So this less than symbol here is specifying IO redirection, right? So you can actually, how IO redirection works is whatever comes immediately after it, that's the file name that you're specifying for it.
So it never takes 2 arguments?
No, it'll never take 2 arguments. So when it sees this, the first thing on the command line, and this is actually pretty valid, is the less than symbol. So it'll be taking input from A, and then it'll be putting it into the command B. So for this one, the command would be B. There would be no arguments. Standard in would be from A, and standard out would be a type. Does that make sense to everybody? Cool. This next one, what would the command be here? This middle part. E, right? Cool. what are its arguments?
F dot G and H.
Right, it has two arguments, f dash g and h. Its input is coming from a pipe from this first command, and its output is to this pipe into the third command. Alright, so for the third command, what would the actual command there be? What, right? Because the first thing is specifying IO redirection, so we'll ignore X, because that's going to be the file name associated with that. So the command is Y. It has one argument, which will be Z, and then its standard input will be coming from a pipe, and its standard output will be going to X, because it's that greater than symbol. Does everybody see that? Cool.
For part E, I saw the argument would be like box and box. Since, I mean, like the second box, the box on the first box is the first argument. The last one is also an argument as well.
Yeah. Did you get marked off for that?
Yes.
Well, you can just bring it to me later and we'll look at it.
Sure.
Okay. Yeah.
Wait, why is the line a command and not just like an option for output and then it just ignores that?
Because so for output, for the IO redirection, it's just going to look at whatever immediately follows the
Yeah.
greater than symbol, right?
So would it just ignore line B?
Well, there's no, you specify the output right here, but there's no command that's been specified yet. So, go ahead. To answer your question. So it defines Y, because it knows X will be associated, or it thinks X will be associated with IO redirection, right? And then the next thing after that will be the command. Because typically it's whatever the first thing is on that command line will be the actual command, because we're specifying the IO redirection first. We look for it later. Cool. All right, any other questions?
On number B, why are the arguments B and D?
So it's that same thing. We have IO redirection right here, and that's going to use the A, right? Then B will be left as an argument, and then we have another IO direction, which will be associated with C, and then that D at the end will be an argument.
The word count doesn't take arguments, does it?
There's still arguments on the command line, though. Yeah. Any other questions? Yeah.
And number 4C, oh not C, just the third black code.
Which one?
And the third code, the last one, number 4.
This one right here?
Yeah.
Okay, so here, you kind of need to step through the whole problem for this one, right? So, up here, this one should hopefully be fairly simple. We have an array with 1, 2, 3 as its values. We set our pointer P equal to the start of that array. And then right here, what will happen is we're dereferencing whatever P is pointing to, right? Which is the first element of that array. And then we increment its value. So this first element right here will now be 2. Okay? And then right here, if we recall, this statement looks like this with parentheses around it, right? So this is actually going to increment the address P is pointing to. So the address of P will move down 1. So that means the answer here would be X is at 100, right? x of 0 is 2, x of 1 is 2, x of 2 is 3. And then finally, p would be 104, because remember, this was declared as a character pointer, but we had that correction for an int, right? And on the online test, we graded it. We were really lenient with this problem on the online test because they didn't have that correction. So, and then star p would be 2. You see that? Okay. So for the second part, what should be the result here?
X should be 100, x of 0 should be 6, x of 1 should be 7, x of 2 is 8.
So I believe it should be, yeah,
So
6, 7, 8.
p is still 104.
Yeah. So then p didn't change, right? So p is still 104. But what is star p?
7.
7, right?
And variables 2.
And variables 2, right? Does everybody see that? Cool. So now that we know all that, let's just copy it and bring it down here. Alright. So what's going to happen here? Let's just write all this down so we have it.
Wait, why is star p 7?
Because what address is it pointing at? What address is p pointing at? It's pointing at 104, right?
Yeah.
And what is 104?
It's the second element of the array.
Right. So the second element in the array became 7, right? And we're still pointing to that same memory address. So star p would be 7. Cool? Alright. So then on this last one, what's going to happen here? So we have this expression right here, right? So on the first iteration, what's going to happen? I will be 0, right? So we'll get pointers plus I mod 4. So 0 mod 4 will be 0, right? So we're dereferencing that, and we're setting it, because this is an array of pointers right here, right? So we're setting the address within that array, whatever address this produces, right? So x plus 0, what should that produce? What value does x have?
100.
100, right? It's memory address 100. So x plus 0 should stay at 100, right? Cool. So on the second iteration, this expression is going to be indexing to that second position of pointers now. Okay? And then we say it's equal to x plus 1. So what address will that produce now? 104, right? Because x is an integer array. So that'll go down 4 bytes. So this is now 104. What should this be? 108. It's just going to go down another 4 bytes. This will be 112. So now we've done 4 iterations of this loop, right? So now we're actually going to reset back to the start of the pointers array, right? So this I mod 4. So when we're at iteration 5, or we're at iteration 4 of this loop, we'll be setting the 0th position of the pointers array again, right? So on the 4th iteration, fourth iteration of the loop. We're setting the 0th position again, right here. So 100 plus 4 with pointer arithmetic. It's an integer pointer, so that'll produce 116, right? So this becomes 116. And then we just move down that whole array again. This is 120, 124, 128. So at this point we've done 8 iterations, right? So we have one more iteration left. So we again loop back to the start, and this is 132. You see that? Cool. So this is the line we deleted right here, so I'll just go ahead and erase that. But what happens right here? We're setting the second address of that pointers array, right? And what what is the address of P? Does anybody remember? So 104 is the address P holds, right? But where is P? What is the address that P is stored at?
Does it have one? Oh.
It's stored at address 200, right? So that means the third position in this array right here is going to be changed to 200. Cool? Does that make sense to everybody? All right. Any other questions on the test? I'll answer one more question about it, and then we're going to start lecture. Nothing? Okay, we'll just start lecture then. Oh, sure.
No one's asking back. Just sorry, I forgot number. Can I have number 6 and I? Oh no, L.
This one right here? So one of them is / dot profile. One is / dot user _ profile. I forget what the third one is. But those are the two that I know off the top of my head. And so those are the files that we talked about how we can customize Bash, right? So those are the files that when we log into Bash via login shell, it looks at those files to see what commands to run on startup. Cool. All right, so let's start the lecture then. Okay. I think I opened the wrong slide. Alright, so this is the slide we left off on right here. So yesterday we started talking about, well, first we talked about pointers to pointers, which is an important concept, especially for things like if you want to have an array of strings in C, that's really a pointer to a pointer, right? Because a string by itself is already just a character pointer, and if you wanted to have an array of strings to represent something, you would have a bunch of pointers to character pointers, right? So pointers to pointers, that's really the most basic example of it, but they are an important concept that are used a lot. So we also started talking about memory allocation. Does anybody remember what function we started talking about that allows us to do this?
Malloc.
Malloc, exactly right. And how does Malloc work? What does it do? Anybody? Yeah.
Allocates which base you want it to view.
Right, what parameter does it take?
And
An int that represents what?
bytes.
The number of bytes you want, right? Exactly. So malloc is a function that reserves memory for us. It takes in an integer for the number of bytes we want, and it returns an address to the start of that memory that it reserved. Okay? Cool. So we talked about just the basic uses of it and kind of some simple examples using it. We left off on this slide where we have this loop that will run forever, and all this is doing is it's just allocating some block of memory and then it's immediately freeing it. So we were kind of rushed at the end of lecture, but we looked at a few of these questions. This we saw performs about 20 million iterations per second. We saw that it would actually run faster if we changed the size to 100,000 that we were allocating. We saw that every call to malloc will return the same. Actually, we didn't look at this, but I told you that every call to malloc in this scenario will return the same address, because it's just going to keep using the same block of memory because we allocate it and then we immediately free it. So how malloc works is just going to keep on using that same block of memory and giving it back to us. So if we remove free, we'll actually eventually run out of memory, and it takes a while. We ran it yesterday and it didn't end up happening, but if you actually print out the address of the function's return value, you'll see that eventually it starts returning null. And that's how you know that the malloc function has run out of memory, or there was an issue allocating that memory, is when it returns null, which is what we say right here. It returns 0, which is equivalent to null. All right. So memory management in C seems simple enough at first glance, which it really is a simple concept. However, it can be extremely detrimental if you aren't careful while doing it. So at first glance, it just seems like free allocated memory whenever you're done with it. But this has many more implications. So if memory is allocated, it must be freed. We can't use memory after it's freed. Something similar is don't free memory that will be used later. Don't free a block of memory more than once. These are all issues that we have to consider when using dynamic memory allocation. So another issue is don't free memory that wasn't allocated, right? So if we declared an array as a local variable and we tried to free it, that would be an error, right? And of course the final one is don't use memory outside the bounds of an allocated block. So this is this kind of simple, okay, yeah, free allocated memory when you're done with it, but then there's all these other issues that we have to deal with when we're using dynamically allocated memory. Some of these also come up when we're using arrays and things that are locally allocated, but we also have to keep it in mind when using functions like malloc. So the fact of it is very difficult to avoid memory management errors in larger C programs. So in this class, programs will be fairly small, probably never write something more than 200 or 300 lines of code. But as you get into larger C programs, if you ever write C programs at a company someday, memory management becomes extremely hard to handle the larger your program gets, and it can also be the cause of security issues and very small bugs in these large programs, right? Yeah.
You free the memory? Do you like free the whole block, or can you free like certain addresses within the block?
You'd have to free a whole block at a time.
At a time?
Yeah. There is a function we'll talk about later that might kind of do what you're talking about, but in terms of malloc, you have to free a whole block at a time.
The memory we use
Yeah.
Okay.
So when you use SSH into Lectura, it's basically like remotely logging in to that computer, right?
Okay.
So every time you run something, there's actually, I think it's like that room across from the advising office over there. That's the server room. I think that's where Lectura is. I'm not 100% sure.
Oh,
But so it's actually logging into that computer, and every command you run, it's running it off of that. Yeah, exactly. And so whenever you run a C program, there's a macro that defines how much space and memory you have when you run it, which you can change, and I think the maximum is 8 gigabytes of memory. By default, I think it's like 2 gigabytes, something like that. So when you run it, that's how much space you have for your program, right? And if you go over using that amount, you'll get stack smashing, which is bad. We'll talk about it later. Cool. Did you have a question too? Okay. Cool. All right, so these are the kind of issues that we have to consider. So let's go and look more specifically at what these issues might look like in these programs we're writing. So a very common type of memory management error is called a memory leak. So a memory leak occurs when memory is no longer needed, but it is not freed. Okay? So here's an extremely obvious memory leak, which is the same example we were just dealing with, right? We just have an infinite for loop where we allocate some block of memory, and then we never free it. So on some iteration of this loop, we'll allocate a block of memory, we'll store its address into P, but then on the next iteration, we'll reassign P to the address of the next block it's allocated, right? So we lost the address of the previous block, so now we'll never be able to free it because we don't know where that block exists anymore. Does everybody see that? We need to maintain the address of the block we allocated in order to eventually free it, because that's the parameter that free takes. And if you recall, when we talked about free, it has to take the address of the start of a block. It can't be off by a little bit. It has to be the same address as the start of a block. So is there a leak in the following code? And if you recall, we worked, oh, I have the answer right up there. So if you recall, we worked on replicate yesterday. And essentially what it does is it takes in a size I in a character A, right? And it creates a string that's I in length, and it fills it with whatever character we passed in, right? So it's calling malloc within that replicate function and returning its address. So I gave it away because I was so anxious to get on with the slide. But yes, the memory allocated by replicate is never freed. So every time we call replicate within this loop, we're not saving its address, right? So we give whatever replicate returns as a parameter to this printf call, right? So it'll allocate some string, fill it with our characters, and print it out. So that's completely legal and that's valid. But now we have this block of memory that's leaking out, right? Because we'll never be able to free it. So if you could think, maybe this for loop's inside of another function, right? Every time we call this function that contains this for loop, we're leaking out however much memory this will allocate, right? Cool. So how could we fix this?
Store a returning value and free it after the printf state.
Exactly. So we store the return value, just like John said. So we call replicate, we get its address that it returns, then we print it out, and then we call free right after we print it out. So it's a very simple fix, right? But you just have to be cognizant of these things because they can happen very easily if you're not careful. You might go, oh, it's way simpler to just write this loop, but you'll lose a lot of memory that way. Cool? All right. There was there's one more thing at the bottom of the slide, but I guess it's not fitting on there. So is there a leak in the following code? If you recall, this is our replicate function that we were talking about. I'm sorry. This is the same exact slide. I guess I meant to move. I separated it out into two and I didn't delete the other one. My bad. Okay. Cool. So here's the fix that we just talked about, and here's that additional thing I thought I had on the last slide. So the user of the replicate is now burdened, right? Because now we have to handle whatever replicate is returning, and we have to make sure to free it, right? Would it be possible for replicate to ever do the free itself? Would there be a way to make it so the user doesn't have to handle it?
Like you wouldn't have to handle it in your for loop.
Right. No, there's not.
So you wouldn't be able to return anything to free.
Right, exactly. So we could technically malloc it and free it in here, but that memory that we just freed within replicate's no longer valid. So if we return it, we might get an error when we're using it within our loop over here, right? Okay. Cool. Does that make sense to everybody? Hopefully I didn't confuse you too much with my poorly made slides. Okay. Here's a coding practice to avoid leaks that's practical in some cases. So this is just kind of a little motto, right? So when you write a call to malloc, immediately write the corresponding call to free. This wouldn't really work, especially like in our last example, right? So what would be the issue applying this practice to our last example? Well, where do we call malloc in our last example? In the function, right? So if we immediately write, we call it in our function and then we return the allocated address. It's like Jesus was just saying, if we call free in our function, that wouldn't work, right? So we have to be careful when doing this, because it's a very common C programming practice to allocate memory within a function and then return that memory back to the user. So the solution to that would be write the free as soon as you write that function call. So again, you just have to be very aware of what's going on with your program when you're doing dynamic memory allocation. Because here, if we didn't realize that replicate was allocating that memory, that would be a memory leak, right? Because we never free it. So you just have to be, again, always thinking about this stuff. If a word processor leaks 1,000 bytes every time you save the document, how likely are you to notice that? Probably not very likely, right? Because I might open up Word, save my document, 25 times as I'm working on it or something, and then close out of it. So when eventually I've closed out of it, that memory is reclaimed by the operating system, so that leak's no longer there. But it's still happening, right? So the bigger and or more frequent a leak, the easier it is to find. So if I leaked, if I leaked 1,000 bytes every time I typed A on my keyboard, my computer would start to slow down really fast, right? So it's kind of like there's different scenarios where a leak may be worse than others, but again, you just always want to make sure you just don't have any. Because leaks can also lead to things like security errors or security issues and such. Cool. A memory leak should never directly cause a programming malfunction, but a malfunction will often result if memory is exhausted. So again, having these little blocks of memory just floating around that we haven't freed will never directly cause programs to malfunction, but a malfunction could result if we start to run out of that memory that we're using. Could there be memory leaks in a Java or Python program?
since you said garbage collector.
Right. So Java has garbage collection, right? So essentially garbage collection works by determining when an object's no longer in use, right? And then it frees up that memory. Python has different forms of automatic memory management, but there's similar things to garbage collection in Python as well. So these things automatically deal with it for us, right? So there'll never be a memory leak issue in these programs. Technically, you could run out of memory, right, if you made enough objects that you were actually using that it didn't free them up, but there'll never be memory leaks where there's just chunks of memory that nobody can reach anymore. Cool? Alright. So here's another example of an error. That should say use after free, not user after free. So if a function returns a pointer to allocated memory, the usual practice is to save the pointer, use the memory, and then free it. So if you remember, this is our loop that we were just looking at. So a common error is to free the memory, then use it. Again, hopefully you are all smart enough to not do this, but there can be more difficult to find cases of this same kind of issue, where you get a block of allocated memory, you free it, and then you try and use it. This is just an extremely obvious one, but it's illustrating the point that this is an error. So right here, our replicate function is returning that pointer to that string it allocated. We immediately free it, and then we try and print it out. So this would be an error. Cool? So this type of error is commonly called use after free. What are likely behaviors for the above code? Would a segmentation fault happen? What do you guys think? Yes? We could try and find out. So let's go here. So we'll put our main function, and then we'll just copy this code in. So I don't know if I haven't really ever said this, but I really encourage you guys, if you ever have questions in C, or if there's something I say in lecture that you find confusing, to just go and try and program it. That's really a good practice throughout all your courses in computer science, is if there's a question like that, just go write a simple program that would illustrate your idea and then see what happens, right? So I do a lot of examples like that in lecture, but I encourage you to do it on your own as well. Okay.
Header files.
Header files, it's true. It will compile without them, but we need them. Okay. So let's try running this. So we just got a bunch of blank output, right? So again, let's look at our code. What we were doing here was we were allocating our memory, right, in this replicate function. Then we immediately freed it, and then we printed it out. So John had suggested maybe there would be a segmentation fault when we tried to print this, but what's actually happening when we run this? It's printing out, well, the new line's coming from our printf call, right? Because we said print the string with a new line at the end. But it's just printing out a bunch of blank memory, right? So it won't necessarily give us a segmentation fault, but we have no idea what will be in that memory anymore after we freed it, because it's no longer ours, right? So in this example, we will have just filled it with A's, but then when we free it, either the free function's doing something with it, or some other program's now using it, and that memory now has different contents inside of it, right? So we just don't have defined behavior after we freed that. Cool? All right. So another type of error is a double free. Per the usual, taking a while to load. Can anybody guess what a double free error is?
Seg abort.
Yeah, I think that's what happens. But like, what is it?
Free it twice.
You free it twice, right? So another common memory management error is to free a block of memory twice, typically due to confusion over which function is responsible for the deallocation of that memory. So if we had this example right here, what's happening is we have this function f, which calls replicate. Okay, it gets that string that we're dealing with. We then call this function g, it prints out our string, and then it frees it, right? And then we come back to our function f, and we free that same block of memory. That will be an issue. So you just have to, again, this is just illustrating another point where you have to be careful when you're managing your memory, right? You have to be sure whose responsibility it is to deallocate that memory that we got from that replicate call. So again, this sort of error is often called double free or multiple free. Does everybody see what's happening there and why that's an issue? Cool. So a different manifestation of confusion of responsibility is a leak. F and G might both assume that the other routine is to free the memory. So kind of the opposite of a double free could be a memory leak, right? Where F says, oh, my G routine is supposed to free it, and G says, oh, whoever called me is supposed to free it, right? So that's kind of another issue that can manifest in this way. Let's go ahead and run this as well, just to see what kind of error it will produce so you guys are familiar with it. So we want to keep that. Let's put our functions f and g in right here. Comment all of this out. And we'll call f within our main, okay? So we'll compile it. What's the declaration?
That's because we put the G.
Oh, because G's after it. Yeah. True. Okay, so we move that. Alright, so if we go ahead and run this, that's kind of weird. So it prints out this weird error message. So first, it printed this out, which that's our print statement within G, right? If we open it up, we saw we printed f of %s, whatever string was passed in, and within f, we created a string that was 10 x's, right? So right here, that's what it's printing out. Oh, I control my command line with my remote. Isn't that cool? So that f of x is what it was printing out. And then right here we get this error in ./a.out, double free or corruption, and then it gives us this memory address, and then it aborts. So what's actually happening here is we're not just getting like a segmentation fault, right? There's actually a useful error message. Whoa, C's finally doing something for us, right? So this is being printed out by that free function. Because again, we talked about malloc, it has a bunch of pools of memory, and it keeps track of what pools and what memory addresses are currently checked out, you could say, right? So when it sees that a memory address has already been returned or freed, and then somebody comes and tries to free it again, it's like, whoa, a double free happened, that's no good, and it prints out this error message, and then it aborts your program for you. Cool? All right. So the last issue we mentioned was freeing non-allocated memory. So another type of error is free memory that wasn't allocated. And here's a simple example. So right here we just declare a character x10 and then we try to call free on x. So yes, x was allocated, right? But it wasn't allocated dynamically. This exists on our stack and that was handled by our compiler. The memory here wasn't created by a call to malloc, right? Or a call to a memory allocation function. It was created in a different place. So when we try and pass that address in to free it, we get an error because free knows that that was never a memory address that was given out. Cool? All right. So a more subtle error is to adjust a pointer that was initially provided by malloc. So this is the same exact issue, although it's, again, more subtle. Because what's happening here is free only accepts a memory address that was returned by malloc, right? Or a memory allocation function. It has to be that same exact memory address. So if you even just give it that memory address +1, that's an error, because it doesn't know that that's associated with the block. It only knows the starting address of those memory blocks it's giving out. So imagine this example. We say P is equal to malloc some memory, some if statement or something, and then we increment what P is pointing at. And then we call free P right after this. This would be an error because even though P is only incremented once, it's no longer pointing at what the original address was, right? So now free doesn't know that that is associated with a memory block, and it spits out an error at us, even though we might think it should be working correctly. So you have to be careful to always pass in that original starting memory address of your block of memory. So again, it's only valid to call free with an exact address produced by malloc. In the above case, if malloc returns 1000 and the block is executed, free is called with 1004, not the address 1000. You could call this freeing an advanced pointer. That might be a better way to put it. Does everybody see that? This is an error that happens a lot. This is probably one of the most often errors you'll find when you're trying to free memory. So free only accepts an address it knows has been given with malloc. Cool. All right. Any questions on those memory errors we were just talking about? Great. So the C11 standard simply says that behavior is undefined for memory management errors. The response of allocators to errors will vary by implementation. A simple example of freeing non-allocated memory, here's its behavior on Lectura. If we had this exact block of code where we allocate some block of memory and we store its address in P, this would be an error because it's not that original address that was returned by malloc, right? So if we run this on Lectura after compiling with GCC, we get this output right here. If we try running our executable, it says glibc detected, a.out, free invalid pointer, then it prints out a backtrace. Okay? On OS X with Clang 6.0, which Clang is another type of C compiler, which was an extra credit question. If we run our executable, we get this message. A.out, some value in a memory address, malloc, error for object, pointer being freed was not allocated, right? So again, this is just illustrating that the standard is just saying that it's undefined what to do if this happens, but compilers like to be nice to us, so they actually tell us what's going on. Cool? Alright. So from the malloc man page, we see when the environment variable malloc underscore check underscore is set, a special implementation of malloc is used, which is designed to be tolerant against simple errors. And notice that it says less efficient, so it will be checking for more errors that are occurring, more memory management errors. It'll handle more things for you, but again, this will be less efficient because it's got to do more stuff now. So again, if we set this environment variable call malloc check, we can have it look for more errors for us. So if we set our environment variable malloc check to 0, any detected heap corruption is silently ignored. Okay? If we set it to 1, a diagnostic message is printed to standard error. If it's 2, abort is immediately called. If it's set to 3, that message is printed and abort is called. So these can be useful when you're writing your programs to help you debug memory issues that might be happening. So one or more environment variables can be set for the duration of a command by specifying whatever variable you're looking at is equal to a value at the start of your command line. And we just want that for this following example. So we could say malloc underscore check underscore equals 0 to set it to not print out, to not do anything if it detects a heap corruption. We could set it to 1, and when we run this, we get glibc detected, invalid free of a pointer. So by default on Lectura, it's set to 1, because these are the kind of messages you guys will see when you run it. If we set it to 2, again, that'll just immediately abort the program whenever it finds heap corruption, so that's what it does right here. If we set it to 3, it prints out a more in-depth message, and it prints out the backtrace. And if we set it to 4, it would do an abort and also print out this error message. So these can help you debug your programs while you're working on them. So you can use echo and $malloc underscore check underscore to see if you've already got it set. You could also put in your /bashrc, you could set it to whatever you want to make it permanently be that value. All right. Cool. So we'll go ahead and take a 5-minute break right now, but any questions before we do? Good. All right. Go to? Sure. It's not encouraged, but yeah.
So what, like, so sometimes you also, there's another type of error, it's like called class error.
Mm-hmm.
Like what are some like probable cause? Some people like online said it's caused due to a laundry issue.
So I'm not 100% sure. I know like a memory bus is something that's more like OS, like the operating system implementation dependent. Like I really don't know, like without looking at the code, but I don't think I've ever really gotten that issue before, but I do know what you're talking about though.
Yeah.
I'm not 100% sure.
But yeah, got this error when I was writing the assignment, but when I just like add up printf, it just magically disappeared.
Really?
Yeah, but I later on like changed the whole thing, and now it just throws a board instead.
So it was just saying like bus error or something?
Yeah, just bus error and nothing. But I check online. Some people say it's due to alignment, but I'm like allocating chart, right?
Mm.
So it's 1 byte. When a chart is 1 byte, so I
Right.
don't see the point of like alignment issue.
Yeah. I don't know. I can look into it and try and talk about it more.
Well, the code is already gone, so
Okay.
probably.
All right. So let's go ahead and jump back in. As soon as the slide loads. So the memory allocators that we're going to work with are typically very complex, but it's actually not very hard to write a simple memory allocator. So here's a simple malloc that I just threw together. So this, first we have a memory pool, not unlike assignment 4, where we had our data array. So we have 1 million bytes of available memory. Then we have this character pointer, which is going to tell us what the address of the next memory pool is. So initially, we just point that at the start of this memory pool array. So then we have our little silly malloc function I implemented, right? So all this says is it takes in the number of bytes that the user wants, and then it does a little bit of pointer arithmetic. So it essentially says if whatever the address of our next pool that we'll give out is, plus the number of bytes we have, is less than or equal to the memory of pool starting address plus the size of memory pool, which will be 100 million, right? So if that memory address we produce by allocating that much space is less than the amount of memory we have left, essentially, then we create a void start block address, which we set to whatever next pool address currently is. We then move next pool address down however many bytes we just handed out, and then we return that block address, right? Otherwise, we say we don't have enough memory and we return 0. Does everybody see how that would work? So essentially, we're just taking in however many bytes we want. We check to see if we have enough space to allocate that many bytes, and then we get the pointer to that pool of memory we're handing out. We move down our pointer for the next block of memory, and then we return that block we were just handing out. So again, this is very simple. Under what circumstances would this work, or I guess a better way to put it is what kind of limitations does this malloc have?
You cannot free it, since you don't keep account of what the address being given out.
Right. Yeah, that's a great answer. There wouldn't really be a good way to free blocks of memory within here because we have no idea. Well, I suppose we could check to see if the memory address was within this array, but we don't really have a good way of signifying how much memory's been freed and stuff like that. We don't have a good data structure to represent what's going on, right? What's another limitation this has? Anybody else?
Size.
The size. We could only allocate 100 million bytes, right? If somebody wanted more than that, we couldn't do it. We could only allocate 100 blocks of 1,000,000 bytes, right? We'll never be able to go beyond that. Of course, we could always change how big we declare this array to be, but that doesn't help us. You know, we want to, again, be able to use all the available memory that we have. So, the total memory throughput is less than 1,000,000 bytes, which can be easily raised. So here's a problem. So again, that was just kind of illustrating how a simple allocator could work. Malloc and the memory allocators that we'll be using are a lot more complex than this, but just to kind of get an idea of the basic concept behind there. All right, so here's a problem. Write a function int star from 2 that'll take essentially a range of integers, and it will return a pointer to an allocated array of integer values that will range from that from value through to inclusive. So assume that from is less than or equal to 2. So an example of usage is we call from 2 with 1 to 3. We store the address it returns into A3. And essentially we want this to point to an array that contains 1, 2, 3. So print ints is just a simple function that I wrote that'll print the number of ints specified right here from whatever memory address is specified right here. So if we had this call right here, this should produce an array with 1, 2, 3 in it. And when we call print ints, it should output 1, 2, 3. Does everybody see that? Cool. All right, so take a minute. I'll leave this slide up right here so you can see what it should do. Take like 2 minutes and try writing this on your own. right. So hopefully everybody's, even not everybody has a solution, but hopefully everybody's had time to think about this. Let's see. I'm gonna call Milo. Do you have any ideas on how we could start to write this? No? Well, so let's think about it. What is this function trying to do? We're given a range of integers, right? And we want to return an allocated array with that range of integers inside of it. So what's the first thing that this function should do?
So we already have the pointer that is equal to malloc.
Say it again?
We already have the pointer equal to malloc.
No, we do not. So all we have is we want a function like this that returns a pointer to an allocated array. So what should the first thing the function do?
Pointer equal to the array.
Equal to what?
The pointer in pointer.
We don't. Sorry. To what int pointer? To what int pointer are you talking about?
We have the range for the pointer.
We have the what?
Can I see the
Yeah.
original question?
All we're passing the from to is a range of integer values that we want. So, right here, what is this function supposed to do?
It's not pointer
Right. So the first thing it should do, like Abby said, should be to allocate memory, right? So we need to have memory to actually store our values into. Okay. So what should the first thing we do be then?
Int pointer is equal to malloc.
Okay. Great. Exactly. The first thing we should do should be to allocate that array, right? So you said an int pointer is equal to malloc. How many bytes do we want?
Int 2 minus from.
Right. Yeah, so that's almost exactly right. So we want 2 minus from plus 1. Because there'll be a difference, like because it's inclusive, right? So if we said 3 minus 1, that would produce 2, but we actually want 3. So we have 2 minus from plus 1. Very good. And then we multiply that by the size of an int, right? So this is that first thing we want to do in this function. We want to actually get the memory that we're storing our int values to. All right, cool. David, do you have any ideas on what we should do after this?
You could do an initialize.
Okay, so what should that look like?
So you could do like for int I is equal to from 2I is less than or equal to 2, and then increment I.
Okay. So I see where you're going with that, and that's very good. That would work. But we're just gonna go with the solution I have up here. But that's exactly right. That should work. So up here, we declare an int pointer, and I start it to the beginning of buff. And then we say while from is less than or equal to 2. Okay? Then within the body of this loop, we're just going to set whatever our pointer p is currently pointing to whatever the value of from currently is. Then we'll increment that value of from. So this will go down that array we just allocated, and it will set the first position to whatever from was passed in as. Then we'll increment the value of from all the way until from is equivalent to 2, right? Cool. And then we got to return buff here. So the whole point of declaring the second pointer was we still need to maintain that original memory address that we allocated, right? So that's why we have 2 integer pointers up here. So after we moved p down, because p is pointing at some way different memory address now, we still have that original address inside of buff. So that's what we return.
So you could
couldn't increment buff because that would change like the
Right.
original address.
So if we just forgot about P and replaced it with buff right here,
Yeah.
and then returned buff, that wouldn't work, right? Because it would be the last memory address of
Gotcha.
that allocated space.
But shouldn't we check if buff equals null first before the value? Since malloc might fail.
Sure, but for brevity's sake on these slides, and well, first of all, you're definitely right. It could fail, but it probably won't happen, especially when we're allocating such a small amount of memory like this. I guess we could be allocating a lot, but and then also for the sake of shortness on the slide, I don't do that check. So
I think in the previous slide you put like 0 at the end.
so I think maybe you're thinking about that function that found the longest string in an array of
Yeah.
strings. So for that function, we said that it worked by taking in an array of strings where it was terminated by a null pointer,
Okay,
right?
gotcha. Okay,
So that was the convention we made up for that particular function.
gotcha.
Cool. So when we return this, this will be now pointing to an array with that range of values we asked for. Does everybody see that? Cool. So a very important assumption that we made on the last slide was that from will always be less than 2. Right? If that wasn't the case, this would not work. So just take note of that.
What did Malik do with that?
Probably return null. Yeah. If you gave it a negative number, I believe it would return null. Well, actually, no, because malloc takes an unsigned integer in. So if you pass in a negative value, it'll interpret that as an unsigned integer. So even though we're entering it as negative, it'll interpret those bits that represent that number as a positive number. So it'll actually end up allocating a lot more space than you want. So, good question. All right, so let's allocate 3 arrays, print each of them, and then clean up those allocations that we've done. So right here, we call from 2 with 1 to 3. What should this print out? If you recall, 2 slides ago, I said print ints just takes a memory address and then a number of integers to print out after that memory address, right? So what should this print out?
1, 2, 3.
1, 2, 3, right? Because we get that array containing 1, 2, 3 from this from 2 call, and it prints out right there. Cool. What should this print out? Yep. So we have -3, -2, -1, 0, 1, 2. So it still works with negative numbers, right? Cool. But what is actually happening here, though? Because if you recall, we say 2 minus from in our malloc call, right? So again, this will do exactly what Abby's question just was, where that would produce a negative value, right? So we have -3 and 2 right here.
That was too positive.
Oh, that would still be positive. That's right. Am I doing the math wrong in my head? Yeah.
2 minus -3, so 5
Minus
plus
-3.
1.
Because it's taking the green.
Right. You're exactly right. I don't know what I was thinking. I'm sorry. It's hard doing math in front of people. All right. So the next call, we have from 2, 100 to 100. So we only want one value in our range. This will still work out, right? What exactly are we doing here? Michael, do you have any ideas? what will that produce?
It's the address of the address before the that's pointer.
Right. So A1 is the start of this array we're getting right here, right? A1 minus 1 is the address right before that array. So we're saying start at one address before this array and print out 3 elements. Do we know what it will print out? Can we say anything about what it will print out?
Doesn't Malik append what a specific value is?
Yes. So we can't really determine what those values will be, but yes. But there's one thing we can guarantee about this output. What is it?
Second element.
The second element, right? The middle one should be 100. Because we're saying go one before the element, go one address before whatever A1 is pointing to, and then print out 3 elements after that address. So this will output 0, 100, and 164. And again, we had no idea how to tell what 0 and 164 would be, but we could always determine that 100 was going to be 100. Does that make sense? All right. Okay, so right here, this is just kind of an interesting technique for deallocating all those. I declared an integer pointer array, and then I set them to all of those addresses that I just got beforehand, right? And then we just have a pointer to a pointer, an integer pointer to a pointer to this array. And then we just have this while loop where we loop through it, and then we free each one of those pointers. Does everybody see that? Cool. All right, any questions about this slide? Awesome. Cool. So, are there any issues with this statement right here? Can anybody see the issue? Memory leak, right. What's happening?
The returning value of from 2 is directly like passing to the print, so it's not like stored anywhere.
Right. So this is a memory leak, because as John said, this is going to produce the address that, this is going to return the address from that malloc call within from 2, and then we'll not be able to store that address anywhere, so we'll never be able to free it. So this is a memory leak, right? So we've lost the address of the allocated block. So would it be good for print ints to free the memory?
But, like, what do you mean by good?
Would that be a good solution to this problem? No?
It kind of like restricts what you're allowed to use print ints on.
Right. What could we not use it on anymore?
Things that aren't using malloc.
Right. We couldn't use print ints with things that aren't using malloc. So if we tried to put a free call somewhere within this print ints function, we could only ever use it with an address that was allocated with malloc, right? So that's not behavior an experienced C programmer would hopefully expect. And then we also couldn't use print ints to print a local non-allocated array, right? Does that make sense to everybody? So another angle, what if free returned the address it was given? So calls could be nested like the following. Would that be good?
No.
Why?
Because, like, those kind of things are, well, free is evaluated before the, or free is called before the premium, so the memory is already free.
Right. So we're using it after it's been freed, right? So that's bad. So this is just kind of, the point of this slide is just to kind of get you to think about these different issues that can come up when you're using these when you're using dynamic memory allocation. Make sense to everybody? Cool. All right. Print ints expects the number of values to print as a second argument, right? We have the pointer to our array, and then we have an integer n to know how many values we want to print out. Could we write a function, print all, that specifically works with the address returned by from to, such that it prints the values in the newly allocated block and does not require a count? Joseph, do you have any ideas? Would this be possible?
What's the question?
So could we write a function called printAll that specifically works with an address returned by from to, such that it prints the values in the array without knowing the count? Is that possible?
I'm not sure.
So this is actually impossible, right? This is the same exact issue we talked about when we were like passing arrays into functions, right? There's no way to get the size of that block of memory. It's just some memory address, and we don't have a size associated with it unless we pass that into the function. Okay? Does that make sense? Okay. Yeah.
I like know the size though.
Yes.
And there's no way to get that information.
There's probably a way to get it, but it would be very complicated, convoluted. So, yeah. But yeah, good question.
Is it possible that print out would work if it was handling characters instead of integers?
So, if we had a terminating 0 in those strings, then yes, right? But we're not. That's the convention for passing around strings in C, right? Is to have that terminating 0 at the end. But it's not necessarily guaranteed that that will be there, because we could just have a character array without that at the end. Cool? Alright. Alright, so consider a function character that returns a character pointer. It's called concat, that returns a dynamically allocated string that contains a concatenation of the strings S1 and S2. We want to be able to use it like this. We have a string S1, we have a string S2. We call concat on them, and we pass the string literal into concat. And then we print out S2, and it prints out concatenate, because it's this string combined with this one. And then if we did concatenate with S2 and S2, we printed it out, what should that print out? Concatenate, right? So we want to write this function that dynamically allocates a string and then concatenates them both together. So this is just an example of how we want to be able to use it. So go ahead and take a minute to try and write this function.
What is the function that reads the memory?
No, we're writing the concat function, and it's going to return a dynamically allocated string. So we've written this concat function before, right? So hopefully it's familiar, the procedure we should use, but we just want it to return a dynamically allocated string now, rather than doing it in place. So let's go ahead and just work on this real quick because we have like 1 minute left. So here's our solution. So we have our function definition. And the first thing that we're going to want to do is, again, because we're returning a dynamically allocated string, we want to allocate that memory, right? So right here, I say I get a pointer to the start of the allocated memory, and we're allocating the length of the first string plus the length of the second string. Don't ask me why I didn't get 2 separate variables for them. I just wrote it like I did. Plus 1 for that terminating null character, right? And then multiplied by the size of a character. So now we have our memory that we know will fit those 2 strings, right? Cool. So then I just use the stir copy library function. We just take whatever was in S1, we put it at the start of that resulting array right here. And then I just use stir copy again, and I say result plus length 1 to skip over that first string, and then I copy it in from S2, and then I return result. That's literally the whole thing, right? Does everybody see how this is working? How this is allocating the memory for the strings and everything? Cool. All right. So on that note, I really wanted to go over this slide today, but we don't have time to do it. So, yeah. Get started on assignment 5. Ask me any questions on Piazza. I have office hours today and tomorrow. And I'll see you guys next week.